All right, so before we start doing conservation laws on control volumes, which is nominally what the chapter is about, um, we need to define a couple of quantities that are related to the flow of fluid. So we've talked about velocity a bunch of times, but we need to formalize a couple of definitions here. So first, let's talk about volumetric flow rate. So here, what I'm interested in is how many, how much time does it take a given size of fluid to travel, so like meters cubed per second, right? So we're going to calculate this in terms of the local fluid velocity. So in like a one-dimensional flow where the fluid's only flowing in one direction and it doesn't really change, the fluid velocity doesn't really change as you go down the pipe, that's actually pretty easy. So like the distance that a fluid particle travels in time delta t is velocity times delta t, and therefore the volume swept is v delta t times a little chunk of area, like dA. So a little element of volume is swept out by v dt dA. And so if I want to calculate how much volume flows through a certain chunk of area in a certain amount of time, I just divide by the time, right? So d volume d time would just be v dA. And if I want to sum over, let's say, like the whole cross section of a pipe, I just integrate, right? So let's define volumetric flow rate using a variable q. For some reason, q is a variable that people often choose to, capital Q is often chosen as a variable to describe flow rate. So let's say that the flow rate Q, volumetric flow rate Q, is just the integral of velocity dA. So that works actually perfectly fine for like one-dimensional flow. And and just to highlight this, the units are meter cubed per second in the case of volumetric flow rate. And so like velocity times area gives the correct units. And in fact, if you had a uniform velocity, the velocity times the area would be exactly the volumetric flow rate. In more complicated situations where the fluid velocity doesn't necessarily travel entirely in the direction of like a pipe system or like the unit of area that you're trying to integrate over, then the only real difference is that you actually only want the component of the velocity that does travel in the direction of the area. So basically, like, you can do the same calculation, but in that case you just have to take the dot product of the velocity with the unit normal, to whatever surface area you're doing that integration over. So in that case, the fluid flow rate is just the integral of v dot n dA for more complicated flows.